Today we continue Maxwell law of distribution of molecular velocities. If there are n number of molecules in a unit volume of a container and c is the magnitude of velocity of a magnitude at any moment, let us UVW are the components of velocity c along axis x, y, z respectively. Then c squared equals to u squared plus v squared plus w squared as equation first. This equation for UVW, if the component of velocity is c plus dc, then accordingly the component along x, y, z will be u plus du, v plus dv and w plus dw respectively. Now if the probability of a given molecule is Fu du, which have velocity component in between u plus du along x-axis. Similarly, for v plus dv, this possibility is given by Fv dv, and for v plus dv, this probability is given by dw, Fw dw along z-axis. So we know that total probability by probability principles is given by the multiple of these all. Then Fu du, Fv dv and Fw dw and this is given by equation 2. And the number of molecules having velocity component in range u plus dv, v plus dv and w plus dv, then this is given by n into this possibility, this probability. This is equation 3. If in any frame of reference we replace x, y, z by UVW, then all the moving molecules can be represented by a dot at point UVW. Then the density of velocity dots is given by total number of molecules dn and the volume element du, dv, dw. So this is the density of velocity, and this is given by n, Fu, Fv, Fw. Since density rho is independent of the direction of the velocity, so rho will be same in all velocity elements at a constant distance c from the origin. It means if at distance c from origin O, the density will be same. So from equation 4, this can be written as, since this is constant rho, and so and Fu, Fv, Fw is equal to constant. Differentiating it, this can be written as, firstly we differentiate it with respect to u, so Fv and Fw remains outside and similarly for dw v, and this is for w. Dividing it by fu, fv, fw, so this equation can be written as like this. But for constant c, if c constant, then from equation first, u square v square plus v square plus w square is constant. Now differentiating this equation, this can be written as u plus du, v plus dv, and w plus dw is equal to 0. Now from equation to combine equation 7 and 8, we use Lagrange method of undetermined multipliers. In this method, we multiply equation 8 by an unknown constant beta, and then equation 8 is added to equation 7, which means beta u plus this one, beta v plus this one, beta w plus this one, and after all we find equation 9 like this: 1 upon fu del fu upon du plus beta u. This is for u. Similarly for v, and similarly for dw. Since du, dw, and since u and v are constant, independent variables, which means they are not dependent to each other, so their differential will also be arbitrary, which means these equations will be 0 for this equation to be satisfied. So this equal to 0, this should be 0, this should be 0, and this should also be 0. Firstly, if we solve equation for u, del fu upon fu plus beta u du. Now to solve this equation, we integrate this first. If we integrate this, then this can be written as this, and beta u del u, this can be written as this. Since this a is integration constant, and here it is taken as negative, so this equation can be written as like this. Since a is constant, so it can be written as another constant like log a. So this equation is finally written as this: log fu upon a, and this is exponential minus beta u square upon 2. Now fu is written as this. This is equation. This is for u. Similarly, if we solve equation v, then we find equation for v, fv, a exponential minus beta v square upon 2, and similarly for w, this can be written as like this. Now if we multiply fu, fv, and fw, then combinedly we can write it as a cube exponential minus beta u square plus v square plus w square upon 2. But from equation 3, number of molecules having velocity component in terms u plus du, v plus dv, and w plus dw, then this number of molecules given by equation 3. Equation 3, this can be put in equation 3, so we can write it as dn barabar this. But density of velocity, if this is divided by du, dw, du, dv, and dw, then we can find density of velocity rho. Finally we got equation this. as of density of velocity dots. Since u square v square plus w square is given by c square, as we saw in equation first, so finally this can be written as like this. Here we note that beta upon 2 is a constant quantity, so we can replace it by another constant b. So rho is equal to NAQ exponential minus beta c square. Here we note that dn is the number of molecules which have velocity component u to u plus dv and all. But if we find number of molecules in between c and c plus dc, then we have to draw two concentric sphere of radii c and c plus dv. Concentric spheres means spheres which have common center. So the volume of sphere between these spheres will be given by 4 pi c square dc. If we multiply this density rho by this, then we can find the number of molecules in between c and c plus dc, which means the dnc is equal to 4 pi c square rho dc, and finally we got this equation. This equation shows the number of molecules in range c and c plus dc. Now we further continue it in next classes. Thank you.